Dear students and participants of the course on railway engineering, in this lecture we are going to discuss other aspects related to the geometrics of tracks. The two things which we are going to start with, they are widening of gauge and the vertical curves. If you remember, in the previous lecture we talked about the transition curves. We looked at how the transition curve can be laid in the field, and then two specific cases, one the compound curve and another one is the reverse curve, they were taken up. Apart from it, the extra clearances which are required on the tracks were discussed. They were related to the provision of super elevation on the track, the leaning of the vehicle towards the inner side. There can be a throw in the inner side or the outer side. There was a leap problem. And then there were requirement to be looked at in terms of clearances when the two tracks are being laid side by side, or the tracks are being laid on the side of a platform. So, those type of extra clearances have been discussed. Now, today we are going to start with the another aspect, that is widening of gauge. If you remember, if you want to correlate it with the roads, there we talk about the extra widening on the curved section. The another thing which we will be discussing will be the gradients. Not all the locations which needs to be connected by a track, they are at the same level. They may be at different levels or different elevations, and so as to connect them, a gradient needs to be set. Now, it is not possible that you can connect two locations wherein the vertical distance between those two locations is very high, but as compared to that the horizontal distance is not that high. So, if you start joining those by a straight connectivity, which we assume is going to be the most economical connectivity, in this case that is not will be the position. So, here what you need to look at up to what particular gradient we can go so as to construct a track, and that also is governed by the locomotives, their hauling powers and the weight which is to be hauled. After that we will be talking about the vertical curves, and we will see that what are the various types of vertical curves which can be provided depending on the type of gradients and connectivities, what can be the length of the vertical curve, and finally how these vertical curves can be set in the field. Now, starting with the widening of gauge. Now, under the normal track conditions, the wheels and flanges they stay clear of the railhead section. If you remember, previously we have discussed about these type of aspects. So, we have a rail section, and on this rail section a wheel is moving So, there is always a clearance between the flange of the wheel and the side of the railhead. So, under normal conditions this will be a case where the wheel will always try to come to its average diameter condition, and in that form the pressure which is going to be induced in the rail section on either side, that will be equal. But when you talk about a curved section, then the conditions are not same. There is a difference. Now, in the case of curved section, we are going to provide the super elevation which we have already discussed, and in that case the rail section will be having different levels. So, this is one level here, this is another level, this is going to be with respect to the super elevation which is being provided. And we discussed then when we have super elevation which is provided here is an equilibrium super elevation which is calculated for an equilibrium speed, and this equilibrium speed we have talked in terms of the speed groups. That means the trains which are moving on those tracks under different speed limits or under different speed, you can say the groupings. There will be trains which are moving at a speed of 40 to 50 kilometers per hour or 50 to 60, 60 to 70, 70 to 80 and so on. So, based on that we calculate this equilibrium speed and that gives us the Kent, equilibrium Kent, and that is being provided here. But the problem here is that all of the trains, they are not moving here at this particular speed, they may be moving at a speed which is high or they may be moving at a speed which is low. And when this happens, then the interaction of this wheel and flange with the rail section is going to be different. Now, you have to go back and you have to recall that what we have discussed in these type of situations, whether the pressure is going to be higher on the inner rail or it is going to be higher on the outer rail, under which particular condition, when the speed is higher than the equilibrium speed or when the speed is lower than the equilibrium speed, the patterns again are going to be different. That means, now when this interaction is changing, there is a force which will be acting. So, if in this case if we talk, so there is a centrifugal force which is going to act outwards, and if the fastenings which are provided so as to contain the rails with the sleepers, they are not good enough and this pressure is higher, lateral forces are higher, there is always a possibility the gauge can widen at that particular location. So, what it says is that the outer wheel flange of the leading axle moves in a straight line and rubs against the rail head when it is on a curved section. So, this is an outer rail. So, what will happen? The flange will come very nearer to the rail head and it will start rubbing this particular section. And when this happens, there will be loss of material, there may be possibility of some other type of defects which may get induced at this particular location. Now, this outer wheel, it travels a longer distance on the leading axle, the situation is opposite on the trailing axle and that is because of the rigidity of the wheelbase. So, what we are saying is that say we have a combination of the wheel and axles being provided in this form. So, there is a wheel base, this is say front axle and this is a trailing axle. So, this is trying to negotiate a curve. So, when this curve is being negotiated, what will happen that the pressure will come more on this side, whereas because of this rigidity the pressure will increase on the inner side on the inner wheel combination. Now, this particular situation when it is happening, which is not same on the front axle and the trailing axle, which are different, it causes the slipping of inside wheel backward and the slipping of outer wheel forward. So, this outer wheel, this is going to slip in this direction and this is slipping in the other direction. So, that is the issue now which is coming up. Now, this causes the wear of the flanges and the rails around the curves and eases the condition. So, here more or more rubbing action, more or more interaction of the wheel and the flange and the rail head, it is going on. So, the wear, as I already discussed, is one of the possibilities which will be there. Now, widening of the gauge helps in the same manner and tends to reduce the wear and tear of the wheel flanges and rails, because now you are providing an opportunity that even if the one of the axle is moving either outwards or inwards, it will not be the flanges of the wheel, they will not be touching or will not be rubbing against the rail head. So, this is the point which we are discussing here. So, we are saying that if we increase this, so this type of a situation which is appearing here will not be there. So, this extra width which is required on the curve is given by a formula here, which is 13 into B plus L the square of that divided by r, where B is the wheel base and can be taken as 6 meters for the broad gauge tracks. L, this is the lap of the flange, how much this flange is putting a lap on the rail head, and it is calculated by a formula given here, which is 0.02 multiplied by the under root of the summation of h square plus and dh. Now, what is h, what is d? Let us look at those issues. So, h here is the depth of the flange below the top of the rail. So, we have already discussed about it. So, it means if a rail section is here, this is the top of the rail, and when the wheel is moving at the top of this rail, then how much is this distance? So, this is a flange. So, this is the distance which we are talking here, h, depth of flange below the top of the rail. D is the diameter of the wheel. So, you have a wheel here. So, the average diameter. So, this average diameter we are talking diameter of the wheel, and r is the radius of the curve, because everything is happening with respect to the curve. So, whatever is the radius, that radius is what we are talking here. So, on the basis of the discussion which we did, we can summarize what are the reasons due to which the widening of the gauge needs to be done. The very first thing is the application of the centrifugal force on the curved sections, and because of that the tendency of the front axle and the outer wheel moving towards the outer rail, whereas the trailing axle will be having the inner wheel moving towards the inner rail, and those particular interactions are creating problem. And this different type of interaction is happening because we have a rigidity of the wheel base. They are not independent, they are being connected in some form. Then the relative distance which is travelled by the wheels. Now, when we say relative distance which is travelled by the wheels, so there is a curved section. I am moving from point A to point B. Obviously, this radius is say r1 and this is r2, where r2 is greater than r1. So, if we talk in terms of the distance which is being moved here, then that particular distance is here L1 and here this is L2. So, if we consider some angle say delta, so in that case the L1 and L2 can be calculated. So, L1 and L2 will be how much? So, it will be radius multiplied by angle delta. Now, here angle delta is constant, but radius is differing. So, it is R1 delta and this is R2 delta. Now, when R2 is greater than R1, so in this case what will happen is that L2 is greater than L1. That means the distance which is going to be moved on the outer rail is more as compared to distance which is being moved on the inner rail. But then how it is possible when we are talking about a system where there is a combination of axle and wheels and they have been connected together. So, this is the front and the trailing condition. So, the distance is going to be fixed and that has been taken care of by way of the provision of the coning of the wheels, because in the case of the coning of the wheel, the diameter here is d2 and here it is d1, where d2 is greater than d1, and when it moves in this direction it means it is moving with respect to the diameter d2, and this is what we have discussed when we were talking about the coning of the wheels. So, when we are talking about this, that there is a relative distance travelled by the wheels, they are different, then the loss of contact between the wheel and rail in the trailing position is one possibility. So, slip of the inner wheel backward and skid of the outer wheel forward is what we needs to take care of, and that is again we have already discussed previously. Now, let us look at numerical how to calculate this extra widening or widening of a gauge. We have a broad gauge track, wheel base is given as 6 meters. The diameter of wheel is 1524 mm. the flange projects 32 mm below the top of the rail. So, and radius of the curve is 168. So, this radius of the curve 168 means we are given r. This flange projects 32 mm below, that means a small h is being given to us, diameter d is here, and we are also being given the wheel base. So, wheel base is say v. Now, the formula which we discussed is 13 into b plus l is square, the square of all of that divided by r. So, considering this, so it is b plus l is square divided by r, wherein the L is to be calculated, B and R has already been given to us, and this L is dependent on small h and capital D and is calculated by using a formula 0.02 into under root of h square divided by dh. So, here again the h and d values are known to us. So, this h is being taken as 3.2, that is in centimeters, and then d again is being taken in centimeters. So, it is 152.4 instead of 1524 mm, and when put the values here, what we get is 0.446 meters. Now, this value of L we are going to place in the equation. So, when put that value in the equation, what we will get is 3.21 centimeters or 32.1 mm. So, that is the widening of the gauge which needs to be done. Now, what are the gauge tolerances which are being adopted on Indian Railways? That is given here. In the case of a straight track, including curves of radius 350 meters for the broad gauge, it is minus 5 mm to plus 3 mm. When we say it is minus 5 mm, it means we are having a tight gauge, whereas when it is plus 3 mm, we are increasing it. So, there is a slacking condition here. And in the case of the curves of radius which are less than 350 meters, again we are talking about the broad gauge, that in that case it is taken as plus 10 mm, that means the slack condition is taken as compared to the tight condition. Now, let us move to the next topic, that is gradients. Now, gradients, these are provided to negotiate the rise or fall in the level of the railway track. So, there is a point A which is at this level, there is a point B which is being provided at another level, and there is a difference of height h between the two. Now, if this connectivity is to be provided, one easiest thing can be that we provide a connectivity straight like this. But depending on what is this angle phi at which we are going up, there is a restriction with respect to that the vehicle which is moving here, the train which is moving here in this direction, whether it can be able to move or not on this particular gradient. And if it is not so, then if we look at in terms of a plan, it may happen that point A is here and point B is here, and then there are contours through which we are trying to move on. So, these contours we need to look at, and therefore, there is a possibility that some circuitous route is going to be adopted so as to reach the point B, considering that the train is able to move on that particular gradient. So, this can be a rise, this can be a fall, it all depends whether you are talking about a movement from A to B or B to A respectively. Now, the rising gradient, obviously it rises the track in the direction of movement, whereas the falling gradient will cause the track to go down in the direction of movement. That is what I said in terms of these arrows, how the changes will be there. Now, this gradient when we are talking can be talked in terms of an angle, or it can be talked in terms of say 1 in n or 1 in x. That means we are saying that we are going up. So, this is if y, then this is the distance n which is being moved, or it can be in percent. So, we can provide the values in percent for the gradient, and when we say percent, say we are saying 2%, that means it is 2 by 100 or it is 1 by 50. So, it comes back to the same condition. So, 1 in n means 1 in 50. So, any of the way can be there so as to represent it. Now, these gradients, this needs to be provided to connect the various stations which are located at different elevations. They follow the natural contours on the ground to the extent possible. So, if the contours are going in this form, they will try to follow the contour and some possibilities. It may happen at some of the cases it is not possible to follow the contour in that manner, because if you keep following you may end up with a very long route. So, in some of the locations it may happen that even if you have followed it here, then you go a bit up and again you follow the contours at that particular location. It reduces the cost of earthwork required if we are going into a form of gradients, if you are going straight. So, there are different type of gradients which can be provided. They are rolling gradient, pusher gradients, momentum gradients and the gradients which are used in the station yards. Now, this rolling gradient is the one which we try to adopt and try to stick to, but if it is not possible then we go to the other gradients. So, what is this rolling gradient? The rolling gradient is, this is determined by the maximum load that a locomotive can haul with maximum permissible speed. That means, if the locomotive is going on this gradient with a certain weight W, then it should be able to move with this permissible speed, whatever is the maximum permissible speed which is being defined. So, the resistance which is being offered by the gradient has already been taken care of and is being incorporated while calculating this value of Vm. Now, an extra pull which is required by the locomotive when it is moving on a gradient, where the gradient angle is say phi or it is theta, it can be denoted in any form. Then in that case, if this force we are talking with which it can haul, so if it is P, then this should be such that it can resist the resistance offered by the gradient, and that is W sin theta, or it can also be written as the W into the gradient value. Now, what are the gradient values which are being defined on Indian Railways for as the rolling gradient for the railway tracks? So, in the case of rolling gradient with one locomotive in plain area, it is 1 in 150 to 1 in 250. Whereas, in the case of hilly areas, it is 1 in 100 to 1 in 150. That means, if this is a limit, either of those in the respective terrain conditions, and if the values are more than this, there may be a requirement of going to have more locomotives than one. So, one locomotive will not help you out. And when we discussed about the traction, when we discussed about the hauling capacity, at that time I have shown you regarding the various tracks at a gradient or in a plane condition, how much load can be carried by say a locomotive or a combination of locomotives, maybe 7, maybe 5, maybe 4, those conditions we have discussed at that time. Now, once the rolling gradient is specified for a section, then all other gradients provided in that section should be flatter than the rolling gradient after making due compensation for the curvature. That means, there may be a possibility that you are on a gradient, but then at the same time there is a curvature also and again a gradient. So, this curvature will induce further resistance. So, this also needs to be taken care of, and at that point there may be a possibility that we need to have some other value, but otherwise as far as possible we should stick to the rolling gradient. The next gradient which we can talk is a momentum gradient. Now, what is happening is that you are providing a rolling gradient which is like this at an angle theta, but if you go along this particular gradient continuously, it is going to result in a very long circuitous route. It is going to increase the cost of construction, it is going to increase the cost of operation, and obviously because the length is more, the maintenance cost is also going to be higher. So, we need to identify, is there a possibility at some location where we can go a bit higher than the rolling gradient, so that we can traverse some more elevation, and then in that form we can reduce the total length which is required for the connectivity between point A and point B. Now, when we try to do this, before doing this, because now there is going to be some compensation with the hauling power which is available to the locomotive and to move at the maximum permissible speed, with that we need to provide some extra force here, and that is what we are talking. So, gradient is steeper than the ruling gradient, that is overcome by the momentum which is gathered while having a run in a plane or a falling gradient in a valley, is what we are talking. So, what we say is that though we have been moving at a ruling gradient, but at some location we have to provide the momentum gradient. So, what we are doing is either we make it flat or we ease it out down, and this flattening or easing out down will provide a momentum here, because when it starts moving in this direction, then the weight which is acting vertically downwards, which will also have a component which is acting in the direction of the movement. So, that momentum once it is being generated, so adequate momentum once it is there, then we can say okay, we are going on a gradient which is momentum gradient. So, with this momentum being attained along with the falling power, this vehicle will be able to reach here, and again it is going to be eased out. So, it uses the additional kinetic energy which is received during the run on a section, as I just told you in the diagram. No obstructions like signals are provided on section where the momentum gradients are provided. It should not happen that you are here and then you are providing a momentum gradient so as to traverse another gradient, and here you provide number of obstructions or you stop the train. Now, if you stop the train, the momentum is lost, and then it will become very difficult for the train to traverse this gradient. So, no such thing needs to be done here or should not be done here, otherwise there is a problem, a critical issue will be there with the train to traverse this gradient. The third type of a gradient is a pusher or a helper gradient, and this pusher or helper gradient, this is further steeper here and it requires extra locomotive. So, we talked about that with one locomotive you can have a value of 1 in 100 to 1 in 150 or 1 in 150 to 1 in 200 depending on what particular terrain we are in. But if it is more, now we need some more help, and that more help in terms of a hauling capacity or a push can come in the way of bringing in another locomotive. So, we will have two locomotives now, and those two locomotives will be moving together. So, we have increased the total power which is available to the overall assembly here. So, it reduces the length of the section and it also reduces the overall cost, obviously, because now the one which you was going with the ruling gradient was like this and there was no possibility maybe of a momentum gradients. So, in this case, because you are traversing more heights in one go, so overall length has reduced, overall cost is going to be reduced. So, some positive aspects are there just by having the combination of a higher gradient with a one more locomotive, two more locomotives or more locomotives being used. So, one such example here is a Darjeeling railway section where this pusher or helper gradients have been provided. In the case of station yards, the gradient which needs to be provided, the reasoning, the requirements of the station yards are very different. There will be a sorting of the wagons, there can be creating a train and dispatching the train or receiving the trains. So, those things are happening there. So, what we try to do that we need to prevent the standing vehicles from rolling and moving away from the yard. It should not happen that the gradient has been provided in such a manner that by virtue of their weight components which are acting in that direction, the vehicle starts moving, the train starts moving or the wagons starts moving. So, this may happen because of the gravity, and this can also happen if it is an open area. So, strong winds can also induce the force, and because of that force it will start moving. Then it reduces additional resistive forces required to start off locomotive to the extent possible, because when you are in a stop position then you require to nullify the inertial effect also. So, locomotive has to work in that direction too. So, desirable maximum value which is being defined in for providing the gradients in the station yards, it is 1 in 400, whereas the recommended as far as the gravity concern is there, it can be 1 in 1000, and this is also okay if you are talking about the drainage requirements. In the case of drainage requirements too, we can go to these type of values. So, the water if it is coming will start just draining out of that particular area under the gravity. Now, the next thing is the grade compensation. Now, what is grade compensation? We discussed about it previously, wherein we said that there is a gradient on which the track is being laid, but at the same time if I look it in the plan, so this is elevation. So, in the plan what we found is that it is a straight track up to this point, and then there is a curve section and then maybe a straight section again. So, there is some portion here where there is an overlap of a gradient and a curvature, and when this overlap of a gradient and curvature is there, that means the two resistances are getting offered. Then what we do is we do a grade compensation, so that by doing that grade compensation, by making it a bit easy, equivalent to the resistance being offered by the curvature, the vehicle will be able to move on that particular gradient. So, it is done to ease out the resistance offered by the combined condition of curvature and the gradient. The gradient on a curved section shall be flatter than the rolling gradient. The minimum of the two values are taken, one is 0.04% per degree of the curve, another one is defined as 70 divided by R for a broad gauge track. So, we can calculate the values with respect to this. So, we have a gradient, so the gradient value will give you 1, and because there is a curvature here, so that is related with the radius R, so that will give you another value here, and then take a minimum of those. Now, let us talk about the vertical curves. Now, here we are talking about the problems with the meeting of two gradients. Say there is a gradient here, this is G1 gradient, and then there is another gradient G2. So, what is happening when this vehicle is moving on this gradient, maybe in this direction or maybe in the other direction. So, there is an angular formation or a kink which causes abrupt change in the forces. So, there is a kink here which has got created because of the combination of two gradients. So, one gradient coming this way and another gradient is going in this form. So, this kink is getting created, and here because of this kink the change in the force will be there. Because if you talk here the components which are going to be there, say if simply I talk about weight itself. So, now the component of this weight will be here in this side with respect to angle theta 2, whereas here with respect to angle theta 1 the component is acting in the other direction. So, at this point as soon as it traverses you have to observe a big change, and because of that there is going to be a rough running of the vehicle on the track. Another problem is when these vehicles are moving on these gradients and their gradients are a bit steeper, then whatever the combination of vehicles which are coming one after the other, because of this particular gradient as well as the application of the brake. So, you are trying to reduce the speed. So, when this application is there, now these all vehicles they will get bunched up. So, it happens mostly in the case of the down gradients. So, they are coming together. So, whatever couplings are there between these two vehicles, they are going to be stressed, compressed here. Now, variation in the tension of couplings on the summits may get induced which may result in the train parting and an uncomfortable ride. Now, when we say here the summits, let us first of all understand what this summit we are talking. We are saying that there is a, say, a gradient G1 going in this form, and then there is another gradient G2 here. The train is moving on this gradient, and obviously on the other side it will be going in this form. So, when it comes on the summit here, then that is what we are talking. So, at this summit, because this connectivity or this connectivity, because of this component of W which is going here or which is going in this direction, these are getting into tension. And there is a possibility that if this tension is very high, then this coupling may open and that will detach the wagons, or because of this particular condition of the tension being induced at the couplings, it can also result in an uncomfortable ride even though their couplings are strong and nothing has got detached. So, this is another issue here. So, what can be the solutions? The solutions are that we connect the two gradients by a smooth vertical curve at the location of the kink. So, if we were talking about this type of a situation, we say okay, let us have a curve here in this form. Therefore, when this curve is being provided, by virtue of the property of that curve, whatever the provision of gradient, super elevation, anything is there, that is going to be induced slowly and slowly, and that is where everything will be okay. So, it will eliminate the rough run, it will provide a smooth comfortable movement. Based on the orientation of the two meeting gradients, the vertical curve can be take up a shape of a summit or a valley. Now, that depends. Now, when we say summit, it is hog. So, this is basically a summit curve, whereas the another one which we have drawn previously, if this is the situation, then this is a valley curve. So, here again we have G1, G2, this is also G1, G2, but if I want to show that how it is changing, so this is positive and this is say also positive, in this case this is negative and say this one is positive. Now, raising gradient is considered as positive and falling gradient is considered as negative. I have already shown that in the diagram. Now, vertical curves are usually provided as circular curves. This allows a uniform rate of change of gradient controlling the rotational acceleration, because we are talking about again in this case, if the train moves at the top of it here, then the force is acting in this direction, this is centrifugal force, whereas in the other case it will be in this direction. So, this rotational acceleration is related with that. So, we have already talked about mv square divided by r. So, where this v square divided by r is a rotational acceleration. Now, vertical curves are provided only at the junction of the grade when the algebraic difference between the grades is equal to or more than 4 mm per meter or 0.40%. That means, this is the value of the algebraic difference. When we say algebraic difference, it means if we have a value of minus G1 and plus G2, the algebraic difference is minus G1 minus plus G2. Or say if we have a plus G1 and minus G2, then it is plus G1 minus G2. So, that is a sort of an algebraic difference we are talking here. And the value has been given. If it is equal to or more than this, then in that case only the vertical curves needs to be provided. If it is less than that, then that means there is no requirement of providing a vertical curve. The kink is not so problematic that it will create problems in terms of uncomfortable ride or tension or compressions on the couplings. The minimum radii of the vertical curve in the broad gauges, they have been defined for the different groups of tracks. For A it is 4000, for B it is 3000, for C, D and E it is 2500 meters. So, here you can see these are the vertical curves, they are being defined as the summit curves. So, this is plus G1 and plus G2, that is the angle by which the deviation is coming, and that deviation is being taken as a algebraic sum. So, this is plus G1 minus plus G2. So, that is where G1 minus G2. Here it is plus G1 minus G2. So, it is plus G1 minus G2, that is why it is G1 plus G2. So, if we take a value of this one as 4% and this value as 2%. So, the what value we get as G is 4 minus 2, that is 2% positive. In this case, if it is say 3% positive and 2% negative. So, it is 3 plus 2 is equals to 5% in this case. Say if this is 3% and this is 0%, then this is 3 minus 0. So, this is 3% value as G. Here if we talk, so this is say 3% negative and this is 4% negative, then the G value is equals to, this is minus 3 plus 4. So, that is plus 1%. So, in all of these cases what you found is that the final value of G is coming as positive. That means, if this algebraic difference which is being taken is coming as positive, then that will denote the summit curve. Now, the another variation of the summit curve can also be there. We can say that this is horizontal. So, this is G is equals to 0 and then there is another G2 here and we are providing a curve between these two. So, this can also be the fifth possibility. Similarly, in the case of valley curves, we have these 4 plus you can make another one, that means here this is horizontal. So, this is 0% as G1 and this is G2 and therefore, the curve can be created in this form. Here again, if we try to look at the values, the same condition remains, the same concept remains. This is minus G1 and minus G2, say this is minus 3% and this is minus 2%. So, G is minus 3, minus 2 is plus 2. So, this is minus 1%. Here if we take, say this is minus 4% and this is minus 3% for an example. So, the G value is minus 4 plus 3, it is minus 1%. Here say if this is 3% and this is 1% and they are again negative. So, it is minus 3 minus 1%. So, G becomes equals to minus 2%. Here in this case, say this is 2% positive and this is positive 3%. So, the G will be how much? 2 minus 3. So, this is minus 1%. So, in all of these cases, one thing which you must have observed is that this G value is coming to be negative, and that means if it is coming negative, it defines that we are talking about a valley curve. So, in case of summit curve, when the train passes over it, it experiences an acceleration in the upward direction, making the train to move faster, because you are talking about a curve in this form and the train is here and centrifugal force is acting upwards in this way. At the same time, the variation in the tension in the couplings is also caused, because here whatever wagons are being coupled, they will feel that tension. In the case of valley curves, the position of the train, say if we are talking here, this is the position of the train. So, this centrifugal force is acting here, but at the same time the weight is also acting here. Here in the previous case, the weight and centrifugal force, they were counteracting with each other. So, here what happens, the position of train with half on upgrade and half on the downgrade. So, that means we are talking with respect to the center line. So, half on the upgrade and half on the downgrade, it compresses the couplings and the buffers. So, whatever connectivities are there, they are going to be compressed here. Once it crosses the sag, it again experiences the tensions in the couplings. So, you can understand the way it is moving. Now, usually we provide a parabolic curve here. The apex of the curve lies at the halfway between the points of intersection on the grade line. Therefore, its RL will be the average elevation of the two tangent points. So, whatever the position is there. So, if it is starting here and ends here, so this is T1, this is T2. So, the RL1 and RL2 will be there. So, the RL of the apex of point here will be RL1 plus RL2 by 2. The rate of change of gradient is restricted here. It should not exceed 0.1% per 30.5 meter chord for the summit curve and 0.05% per 30.5 meter chord for the valley curves. So, this is another thing which can be kept in mind, and this will allow you to calculate the length of the vertical curves. So, the length of the vertical curves, required length for achieving the maximum permissible speed, that is with respect to the two gradients Gi and Gj, an algebraic sum of that. So, Gi minus Gj into, this is for a 30.5 meter length, and for finding out for the rate of change of grade as r. So, the formula becomes Gi minus Gj into 30.5 divided by r. The new method, it says that it can be calculated by the formula given here, which is Gi minus Gj into r divided by 100, where r is the radius of the vertical curve. As per the existing provisions, we have talked that the radius of vertical curve, what should be the value, 4000, 3000, 2500. We remember whether it is a minimum value or it is a maximum value. Gi minus Gj, this is the difference in the percentage gradients expressed in radians finally. When the difference is positive, it forms summit curve, and when it is negative, it forms a sag curve. I have already shown you that. Now, let us set the vertical curve in the field. There are two methods, tangent correction method and chord deflection method. Tangent correction method is simpler, and usually it is used in the field for the laying of the vertical curve. Now, what is the process? Process is, first of all, calculate the length of the vertical curve, calculate the RL of the tangent points, that is point A, point B. So, RL of A, RL of B, and then the RL of the apex. So, the RL of the apex is nothing but it is a average of the two. Then compute the tangent corrections. So, tangent corrections are required because with respect to tangent, how this is deviating, that is what we are talking. So, this tangent correction is what? Y is equals to Cx square. So, y is the ordinate, this is the vertical ordinate from the chord. So, this is a chord here, and Cx square, C is based on the two grades which are being given. So, it is G1 minus G2 divided by 4n, where n is the number of chords up to the half of the length of the curve. So, if this is the half of the length of the curve L by 2, what are the total number of chords which will be here or here? So, that n we are talking. So, elevation of the stations on the curve, they are calculated by algebraically adding the tangent correction on the tangent. So, if we add the tangent correction here, we will get the points here. So, that is a vertical ordinate we are talking. Now, talking about the changes of the points, the change of point A, this is a change of intersection which is known to us, and then you go back and you are going by a distance half of the length of the curve. Similarly, if talking about the change of point B here, so in this case from the point of intersection you are going ahead with L by 2. So, it is minus L by 2 and plus L by 2, that is the change. Reduced levels, reduced level of point A is the reduced level of point O minus L by 2 into G divided by 100, where G is the gradient which is on this side. So, you have a rate, this L by 2 is the distance by which you are going down. So, that is where if this RL is known to you, you can find out the RL of A. Similarly, the RL of B can be calculated, but here the gradient will be G2. Now, increase in RL for length of curve L is equals to RL of B minus RL of A. So, RL of A and B is now known to you. If you take a difference of that, that is the change in the RL. In this diagram, you may be feeling that they are at the same level, but it may happen that A and B are like this, and then the curve is going in this form, and that is how G1 and G2 may be there. So, what you found is that there is a difference here in the RLs. So, this is an RL A, this is RL B. So, that is what it is talking, increase in the RL for length of curve L, because this length is L, on that is the change. So, once it is known, now if you have to find out for a chord length. So, chord length means you are talking between A and C. So, this is chord C. So, for that C it will be increase in RL for the length L multiplied by C divided by capital L. So, with respect to L this was the value. So, for 1 it is the value divided by difference divided by the length L, and for the distance C it is multiplied by C, that is the simple thing. So, first offset on the vertical curve, that will be calculated by C into L minus C divided by 2R. So, that is an offset we are considering. So, likewise we will have different values of C, we are going to divide it into parts, that is what we are talking 0.2 L, 0.4 L and so up to L. The RL of point on curve. So, now you have got a point here, these are the points on the curve. So, what is the RL of this? The RL of point on curve is RL of point on the grade line plus offset. That means, if I am going in this diagram, so I have come here, this is my point C. So, this point C is basically here on the grade line. So, this is a grade line which is connecting point A and point B, which are having at a distance or at a height of h. So, now you can find out this RL of this point because you know the distance C. So, once this is known, from there we are considering the offset, where RL of point is RL of the previous say A plus increase in RL for C. So, that is what I just defined here. Now, let us look at the numerical here. Consider the data given us gradients, one is the rising 1 in 100, another is the falling 1 in 200. So, there is a rising and there is a falling gradient. So, this is G1 which is 1 in 100 positive, and this is G2 which is falling 1 in 200 negative. We have to calculate the length of the vertical curve which is to be provided here. So, gradient is being converted here in terms of a percent. So, it is plus 1% and minus 0.5%. Now, when take the value of this gradient G, it is algebraic sum. So, it is plus 1% minus 0.5%. So, that value will be there. So, when we get it, we get 1.5%. Now, the rate of change of the summit curve is 0.1%, which is being discussed previously. So, the length of the vertical curve on the basis of that, because this was for a length of 30.5 meter chord. So, with respect to that, for a value of 1.5%, what we get is 457.5 meters. So, that is the length of the vertical curve which is to be provided. So, we close now our discussion. What we discussed, the very first one was the widening of the gauge, various reasons why this needs to be done, and then how we can calculate that widening. Then we started discussing about the gradients, the utility of the gradients, the types of the gradients. Then we shifted to the provision of the vertical curve so as to solve the problems which are being posed by the provision of gradients. We have looked at the calculation of the length of the vertical curve, the various types of vertical curves, how they can be set in the field, and we have also gone through a numerical on that. With this we stop here. Thank you. We will be meeting in the next lecture.